Hello, everyone. Hello. Welcome. I'm Rich Lappenbusch with Supermicro, and I'm going to be speaking with you about liquid-cooled AI cluster architectures, which should take about 3 hours, but we have 15 minutes. So we're going to move through a lot of very thick slides. You will have access to these slides later, and even better, you have access to the people who wrote the slides out at our booth. So if you have any questions, the booth is the best place to get those answered and take a look at what we have. For those of you who don't know, Supermicro is a corporation running annual at about 10 billion plus right now. We've been on a rapid growth curve. We're approximately 6 million square feet under management, 6,000 headcount. And we're organized in 3 primary locations today. There's our Silicon Valley headquarters in San Jose, in the Netherlands, and in Taiwan. We'll be adding in Malaysia here in the next 1 or 2 quarters. We have a production capacity of approximately 5,000 racks and approximately 1,200 liquid cooled. We have, to distinguish us from other folks who build infrastructure, we have a very broad range. We've been doing this for 30 years. We've started out building motherboards and single servers and have graduated and evolved from there based on customer feedback. And so that customer feedback stretches us across a very broad continuum of demand. And I'm not even going to try to go into all the product family lines we have, but suffice to say, whether you want it on a telephone pole, or whether you want to sink it in a tub, or whether you want to put it in a rack, Supermicro probably has a solution there with our partners to get you there. The primary advantage we have is we have the ability to design the product, the motherboard, design the power supply, design the network interface cards from scratch. And we also manufacture that ourselves. So that gives us incredible ability to move and pivot very fast based on customer feedback. It also gives us the ability to hold the stock ourselves, build it, and service it. Those 4 things combined give us an incredible rapid deployment time frame. So we can get to a customer site in weeks where others might take months. Now let's get to the heart of the matter. There are a few factors happening at the same exact time. The first is AI is no longer the domain of a few people in academia and the military. It's now gone commercial. And these AI large language models, the ability for a model to give some value, these models are growing incredibly large. Some of the largest are in the trillions. But even the average size of the AI models that people need commercially to solve their problems is growing rapidly as well. We've seen 50, 60, 70% CAGR on the size of these models that they're building. And that may be understated because we have a limited understanding of how fast they would grow the model if they didn't run out of network or hardware or things like that. So the first thing to understand is the size of these models is growing exceptionally fast. In addition to that, trying to catch up with it, the chips are growing. They're growing in power. They're growing in physical size. The physical size of these CPUs, these GPUs, is noticeably larger than even a few years ago. And of course, the TDP, or the wattage that each chip consumes at peak, is going way up. The other thing to know about AI is, for the first time, it actually runs at peak. The AI systems will go all the way up to 99% if they can. In the past, data centers planned on many of these servers only operating at idle, maybe 9%, maybe 30%, maybe 50%, but not all the systems were going to run at 99%. And that's changing the way people plan for power, the way they plan for network, wide variety of different things. So those 2 things combined mean we have a problem with data center heat. And that is not a problem that's going to go away. The models are going up, chips are going up, and at the same exact time, here in Europe, we have new demands to report on the way we use the resources that we have, the water, the power, the carbon that's embedded inside these products. So even yet another vector is coming in and constraining the situation, which is throttling performance and slowing down the ability for these models to learn. How do you catch up? You upgrade hardware. One of the solutions we have right now, not the only solution, there are a lot of solutions out there. One of the solutions we've adopted right now is direct-to-chip liquid cooling. And for those of you who don't know, effectively, you have a rack of servers. They are given a water feed, and that water feed or that coolant feed is used to pass over and through the chips that are generating most of the heat. Sometimes the memory as well, but most of the time it's the CPU and the GPU. And that water is heated up 10, 20 degrees Celsius, rolls down to a cooling distribution unit at the base of the rack in our design. Sometimes, as you just saw, Rital just showed, it's at the end of the rack. But somewhere near the rack is a CDU. And that will have a facility water loop, a different water loop. And that'll go out to a cooling tower or a liquid-to-liquid heat transfer mechanism of some sort. But in this case, we've shown air-based liquid cooling tower. And that will then, through a process of using evaporative cooling and other things, will cool that hot water back down 10 to 20 degrees Celsius, so that can loop back into the racks, and we have a continuous cycle. To do that, you have to have very well-designed cold plates that fit as a cap right on top of the chips. And of course, the chips aren't the same size, so you have to have a different cold plate designed for each chip. There are a lot of people who've been designing cold plates. What we're showing here is there's a dual proc cold plate right there. There's our X13, which is for a single Intel chip. There's our H13, which is for a single AMD chip, and the NVIDIA H100. You'll notice that they're designed to take different heat loads from 300 to 700. And this is really just the first generation of what's going to happen over time. So of those 300 systems I mentioned that we have out there in the product line today, we have over a dozen now that are designed for direct-to-chip liquid cooling. And those are primarily in GPU and high-density compute. You'll see that for AMD, Intel, and NVIDIA. You'll see that with PCIe cards and then custom configured network interfaces of various types. And the three product lines that accompany that are the Hyper, the Big Twin, and the Superblade. Because one thing that people forget is that as soon as you start this AI learning, you quickly realize you want to, just as we do with our laptops, you want to keep and save the last few versions of something. Well, the size of these these models is huge, and so you quickly need to find a way to store and retrieve these models. And so Superblades and storage-optimized systems that can rapidly get into an AI system, clone that data, and get it back out are important. Here's a quick overview of some of the liquid-cooled racks we have. Often is the case, you're not going to buy one AI server. That's not probably going to meet your needs. You will typically have racks and racks of nodes of AI servers. Those nodes are built in 64, 128, 256, 512 nodes at a time. And they're organized into rack-based systems today because we're trying to follow the industry standards of what we have today. You'll see that with NVIDIA. You'll see that with blade systems. And I've also shown here just kind of the back of the rack because a lot of people don't and haven't seen this before, but the diagram that shows how the tubing is pulling that hot water and cold water back out and through the rack system. In this case, hoses are going out the top. They don't have to. They can also go through the base. So within a liquid-cooled rack, we have several different components, and I'm going to touch on each one really briefly. Going clockwise, the cold plate I talked a little bit about, that will get affixed on top of the CPUs, and usually the GPUs, and occasionally the memory as well. Sometimes it's not a cold plate, sometimes it's more like a blanket with memory, but most of the time it's a cold plate. Then that works in conjunction with a CDU. In this case, we have a 100 kilowatt CDU that sits right at the base of the rack and has multiple pumps and basically keeps all the fluid moving from the rack back out to the facility water loop and the tower. To do all that, you need a cooling distribution manifold. So we have a system that's built and designed to bolt right to the side of the back of the rack, and it's got red and blue connectors. And it's really simple. You either have hot water or cold water connectors, and you use that to connect in just as you would a power distribution unit on the back of a rack. And then finally, you need a hose kit, because you need to hook this thing up to the facility's water loop, and they will typically have a particular type of connector that you need to use. If you don't have all that facility water loop, you will quickly realize you need a way to cool down all this hot water. And one of the ways we do that is through a cooling tower. And so we have been manufacturing this year our Supermicro liquid cooling tower. And this gives customers the ability to deploy an average-sized AI system with a cooling tower rapidly. There's a lot of interoperability between cooling towers and facility water loops, and there's no lack of vendors who can provide that. But it often is the case we're finding that AI is being forced to go not necessarily into a data center or somewhere else because the power is there. So it's often driving an uncomfortable decision about where should the AI system go. Last but not least, you need a system of software to track all the telemetry coming off everything I've just told you. You definitely want to measure the temperature. You definitely want to understand the flow rates. You want to understand if your pumps are working, in addition to everything else you would normally track through a set of servers. And we have a product called SuperCloud Composer, and it has a liquid cooling consult module. And that gives you the ability to see the pumps are working, see the flow rate, see how many hours are on those pumps, see how many, what the load is on the pumps, what the load is on the cards inside the servers. So you might want to understand why GPU 6 is running too hot versus the other 7 that are in there. You have to be able to measure it if you want to manage it. And these are exceptionally complex systems. They are 3 times as complex as maybe a server that was shipped 3 years ago. So here are the top GPU product families. We have the NVIDIA NGX HGX system. Then we have the PCIe systems, which are more just running straight off the motherboard. And then we have the NVIDIA MGX systems. And we give the customer a wide variety of choice with CPUs, with GPUs, and all sorts of combinations therein. Obviously, these are all available in air-cooled as well, but many customers are choosing liquid-cooled, direct-to-chip, as well as working on immersion deployments and figuring out what they're comfortable with in risk and reward. Obviously, the risk is this stuff might not work, this is all brand new. It's usually fear of the unknown. But really the reward is, hey, I get to save 10, 20, 30, 40% off my power bill. And depending on your locality and the location of your servers, that power bill might be quite egregious and difficult right now. So these get clustered into clusters, and so it is often the case that you will want a lot of these nodes to work in concert with each other, not necessarily connected to the internet, usually closed off in a corner, somewhere they have no network congestion, they can just focus on what they want to do, which is learning in the model. We work very hard with our customers and with all vendors I've mentioned already to figure out how to optimize that, both from a software stack standpoint, from a network operating system standpoint. And we're really not going to touch much on the networking, but suffice to say networking is a critical component of organizing these clusters. Supermicro has also been working with Intel on the Goguey system, which is a more broad accelerator. So it can be used for AI. It can also be used for a lot of other things. What's interesting is it's instrumented, and you have the capability of controlling it through the Intel One API, which is one API for your developers to go figure out how to build models and how to build platforms and how to build solutions that aren't necessarily off-the-shelf AI problems. We've been working with Goguey since 21, and it's now just recently announced Goguey 3 will be out this year, along with new Intel CPUs to go with it. The main advantage is rapid deployment. So these are smaller, faster cards. If Intel has a claim, it's 1.5x better than NVIDIA. It depends on the models. It depends on the platform. It depends on the problem you're trying to solve. But there are great alternatives, and this is where it's important to get involved with people who understand how to mix and match and how to think about the different things you might want out of one of these AI deployments. We do have this one at the booth, the 8125. This is a 300-pound monster. This thing has 8 of these MI300X AMD CPUs in it. I encourage you to go see it. It's an impressive box. This thing, typically people will only put about 4 of these in a rack because they actually start to get concerned about the rack itself. Like it's rated at, so many kilos, so many pounds, but can it really handle it? And so this is an interesting challenge in weight. So when you start to think, now this one is air-cooled, it's got the fans, but it also comes in a liquid-cooled version as well. One thing we do more and more and more for our customers is rack-scale solutions. Once people understand what the right platform is for their AI, what they do is they will work with us in a consultation phase to figure out the design, the assembly. Typically they have testing, but this is more hardware testing. We'll work on deployment and support. It's a critical part of the AI deployment because, again, there's not a lot of spare parts. There's not a lot of opportunities out there. I'm going to skip through this because I'm already past time, but I do want to share with you, a lot of people ask me, Rich, what is this? How reliable is this? What can I expect after I've run this for a few years? And we have the luxury of sharing, one of our customers from 5 years ago deployed a full immersion. So not direct-to-chip, but an immersion deployment. And this data here gives you the understanding of actually, when you have a good design, how well this stuff can work. Over 4.5 years, TAC, the University of Texas Austin Advanced Computing Center, they ran these Supermicro motherboards with Intel chips, Intel hard disks, and Supermicro heat sinks, ran it with Samsung memory, and put NVIDIA Quadro RTX 5000 GPUs in there. This was pretty hot stuff 5 years ago, but today this is like, an Xbox. But the point is, they ran it for 4.5 years, and they got some incredible results, which are some of these components with 90 servers didn't fail. Some just didn't fail at all, which was unheard of. So even in an air-cooled system, you would expect 1, 2, 3, 4, 5% failure in air-cooled systems. And we know that because there's a tide chart that tells us some of the thermal problems with even the best designed data centers. Ended up being about 1% annual failure rate in immersion circa 5 years ago, before anyone really knew what they were doing. And so we've been getting progressively better over 5 years. And so we anticipate seeing much lower failure rates than people have generally accepted might happen in immersion cooling. So we have a total liquid cooling solution. It can work, all in one Supermicro, or you can mix and match vendors at any point. We do that all the time. We have components, we have systems, Then we can take it to the rack, we can fill it with CDU, we can bring a cooling tower in, and we can bring the software to integrate all this. The software, by the way, works with almost all the other competitors and collaborators out there. And the whole goal is we'd like to find the energy savings of 30 to 50% for our customers. So what can you expect? We ran a TCO model, and this TCO model gives us, we run a lot of TCO models for our customers to help them understand and estimate what they might see. In this case, we took an air-cooled system and a direct-to-chip liquid-cooled system and made it as similar as possible. What we ended up getting was 280 watts savings with 39% lower rack power. PUE went down to 1.09, which achieved 18,000 in savings per year per rack, which is impressive given the lower power rates in the States right now. So one of the things I'd encourage you to think about in any of your deployments is running TCO models and also running total cost of the environment models as well to understand what this might be in water, power, carbon, and other things out there. So that's it. Thank you. Love to take questions. Yeah. No questions? All right. Thank you. Oh, there is one. Yeah.
What will it take for your customers to make a leap towards immersion?
Well, 5% of them have already decided to jump. So sometimes it's getting the card they want, in the coolant they want, in the tank they want. It's a little bit of a hodgepodge right now. So a lot of them are working with their system integrators to find out. I think a lot of people just need to come to shows like this and see that it's actually working. We saw some tanks on the floor. I think a lot of people need to consider, in some areas their power costs are not so bad. So the pain is not as difficult right now. In other areas like Germany, power rates are skyrocketing. It's a very difficult environment. So to each his own. It's a very different answer depending on where you live, where your servers live, and what your challenges are. But it is happening. It's moving about as fast as everybody can keep up. Other questions? Okay, thank you.